Yeah, I didn't follow those details. So my students, we had been using modules, and students got really frustrated with, this definition's already included, and so I had to walk this tightrope of import and export and include. Sorry, the question was, Verity uses type classes. Why not modules? And the answer is that the students were frustrated. They switched to type classes, and they found out that the system built faster. So I think that at the time, it just opened up more parallelism. Yeah, so there's a guy, Carl Palmskog. He has a paper at ISTA this year. He had a tool demo at ICSE, and he's been hacking a lot on, how do you manage really large Coq projects? And one of his favorite things is Appel's second axiom, which is that you always run Coq in 32-bit mode. I don't know if people know this hack, but it turns out that it's a lot faster. Yeah?
I have a different answer to Michael's question, and I think I'll try to reinterpret the question a bit. So we know that you can model finite maps basically as an algebra link signature and Coq, and then give many different implementations of finite maps, and then have development parameterized over finite map implementation. That makes sense because finite maps are a pure functional data structure. The network here is not a pure functional data structure. At least that's not how we're going to implement it in OCaml. So that approach doesn't work well. We want to define semantics literally because they're not going to be extracted. They're just for proof purposes. And we couldn't actually talk about the network as a data structure. We have to use something like operational semantics to understand it.
So do people follow those details? Adam made an important point, right? So here is different from that, we had that bind code. We're like, what happens if we get bind wrong? Well, we'd figure it out, right? Because we'd have some top-level spec, and we wouldn't be able to prove it if it was wrong. As long as our spec is right, you can't make a mistake. You can't screw up. That's not true here anymore. Right? Now we're playing a different game.
It is true, because this is the spec.
Yeah, that's right. Yeah, so the claim is that you can't screw up, right? If your spec is right, your code is right. That's still true. This is the part where you can get the if the spec is right part wrong, right? So what are we doing right now? Right? We have some beliefs about how the world works, and we're trying to encode them. Now, I think Adam's going to point out that our beliefs might be wrong, and we can make a mistake in the spec that actually corresponds to the way that real world actually works. But this seems like it's getting a little, involved. Right? So now what we're doing is, in our hearts, we have some belief about what networks do. We're going to take that from our hearts, we're going to put it in an Emacs buffer so we can do proofs against it, right? Okay, so first off, we're going to define what sort of externally visible behavior of this system looks like. Right? This is what specs are usually going to be about. What do clients see? Right? In the fresh system, we want to talk about the experience that the client has when they interact with that server. So first off, we want to define a notion of a client event, which is pretty simple. It's either an input that some node got from a client, or it's an output that some node sent to a client. Right? So there's the two kinds of client events. And now we can define the state of the entire world. And for our purposes, what that includes is some mapping from nodes to their local states, as well as the set of packets that are currently in flight in the network. And then finally, the trace, right? And this includes all of these client events that have happened so far. And the reason this is nice to keep track of is it's going to make it easy to write specs. We can write something about all the interactions that we've had with the client and ensure that those look good. Okay, here's some stuff. We're just going to cheat a little bit, and we're going to use, actually it's not cheating at all. We're just going to use functions for a map. We have some other noise for decidable quality of packets. But what's nice is that now we can actually define our first network semantics. All right? So here we have this ideal step. This is kind of the canonical idea. When you just sit down, you're sort of in your common steady state thinking about what your code does when it runs on the network. If you're not a distributed systems engineer, if you're like me, this is sort of what you think about. Right, so there's really two things that can happen here. One is that we can get some input from a client. So some node's going to get some input, and it's going to run its input handler on that, right? Which is going to give us back, it's a handler, So it gives us back a new state, some messages to put on the network, and some responses to send back to that client. And then all we do is we just update this node's state and the map of all states for nodes. We're going to put the messages that it produced in the network as well, and we're going to record in the trace that we had this interaction with that client. Right? So this is pretty dead simple. Now we're going to take a little bit more care in the ideal message. Right? So this constructor corresponds to what we think happens when we get a message from the network. So basically, if the oldest message in the network is P, and we deliver that to its destination, giving its message, and we run the handler for that node here in handle message, and we get back some new state, some messages, and some outputs. Then what we'll say is that the world that had that packet steps to this new world where we've put the updated state in for that node. We've put all of the new output messages in the sort of freshest part of the network. And we've recorded our interaction with the client. In this case, it's none. There's that helper trace IO at the top. In this case, it's none because we didn't get an input. But we still might send outputs, right? I might get a message from another node that causes me to tell my client something. Okay. So what property, what order do messages get delivered in this network, in this model of a network?
The entire the world's list of messages acts like a queue because you're prefending to the front in ideal input and you're taking from the last element in ideal step.
Yeah, exactly. So this is an in-order delivery, right? So the oldest message in the network gets delivered first. This is actually very powerful, right? Because if you know something about how the implementations of other nodes, you can conclude a lot from the fact that you got a message. Right? You can conclude things about the state of the network.
This also seems to assume away errors or failed delivery, duplication, and so on.
Oh yeah. Yeah, this is grossly unrealistic. But I actually don't think it's that far from what a lot of people would like to program it. Right? It would sure be nice if when you were programming, you could imagine the networks behave this way. It'd be a lot easier to reason about your code. Right? And so our goal is going to at a high level, try to be to basically enable programmers to verify their code in this semantics, but actually run their code on real networks, but have a guarantee that it behaves as if it was in the nice semantics. And that won't quite be true, but we'll get a little bit close to it. Okay, great. So what have we done so far? We figured out how we're going to model, how we're going to define implementations of distributed systems. Right, we've seen an implementation of a distributed system, and now we have semantics for distributed systems. So we can talk about what they do. Now down here at the bottom, we have all the sort of, normal stuff. There's the initial world, and there's a reflexive transitive closure of the steps. There's a little exercise in here. This is a fun one because these two things go in different ways. So these different notions of reachable, we have one that's with the REFL star. We have one where we've sort of inlined it and baked it in, but it happens on the other side, right? Instead of growing from the left, it grows from the right. This is a good exercise if you've never done it before. But at a high level, we have some semantics, right? We can talk about the set of states that a distributed system could ever enter, right? Which means we can prove things about distributed systems now. So let's try to prove something about our fresh system. Okay, how are we doing? Where's Leonard? Is it 10:30? Yeah. Okay. In the interest of time, well, okay, let's do this. What should my fresh system spec be? Please.
Series of messages it sends out or incrementing nationals at high level.
So it sends out, but remember there are no messages in this system. I mean, I'm being pedantic, but
Input requests.
Outputs, yeah, you're absolutely right. And how are we going to write that down? What are we going to get our hand on to write down exactly this property that you said, right? That there's sort of no repeats, no duplicates in the outputs.
Trace.
There you go. Great. Thanks. Awesome. Okay, so we have a couple of helpers here. Basically, the first thing we're going to do is we're just going to write something that kind of filters the trace and makes it nice. It's going to go through the trace, and it's going to pull out all of the natural numbers in outputs. Right? We're going to collect that up. And then it's pretty simple to write the spec, right? We pull all of those out of the trace, and then we just want to know that there are no duplicates. Okay.
Can we prove the much stronger thing that it's going to be the list 0 to n in order?
For this system, yeah. So one thing to note, right, is that so a lot of times when you're defining semantics or something, you shouldn't actually, well, I mean, it depends a little on the system, but you should think twice before you reach for defining a relation. A lot of times it's really nice, actually, if you can define an interpreter. Here, though, we needed to define it as a relation, right, because there's a lot of non-determinism. Except, remember, in our fresh system, there are no messages, which means that we don't have this case. Which means there's only one thing that can happen. Right? And there's still non-determinism because we don't know what inputs we get. Right? But given a set of inputs, there's exactly one output this system can produce. So yeah, we could prove something stronger.
But it would be wrong.
Why?
Because then you've overspecified it. You have no flexibility to adjust the implementation to run in parallel on many nodes, handing out different batches of natural numbers.
Yeah, so this is a great point, right? Did everybody follow? So we could prove something stronger, right? We actually could prove a spec that would essentially allow exactly one implementation that did exactly what it did. And then we would be very confident that we'd written down the same mistakes twice if we had any. Instead, right, we're really writing down what we care about, which is that from the client's perspective, right, if you get something from Fresh, nobody else has ever gotten it. That number is yours, right? It's never been given to anybody else. You know it, right? There's no dupes in the outputs. Right? Nobody else will also, we haven't written it down this way, but you also know nobody else will ever be given that. So for any state this system might reach, there'll still be no dupes in the output. And that's more flexible, as Andrew was saying, than if we'd said it's this increasing sequence. Yeah, okay. So let's prove it.
I have a problem with the specification.
Tell me.
It allows the implementation.
Ah, yes. No, yeah, right. Yeah, it does. And in fact, we'll make a point about that, but we're not, I mean, there's...
Can you say what is the point? Because
liveness, I think.
No.
Oh.
It allows an implementation that has an empty input handler and does nothing, right? It never outputs wrong answers.
Yeah, it's not live, right? It never does a good thing. There's no guarantee that eventually you get a response from the system.
I guess it's a technical quibble whether we have to say that's not a safety property.
Sure. I mean, I don't think there's a lot of liveness properties that you can't encode as some kind of safety property, right? There's usually some timeout in practice that you could just count down on for the vast majority of cases. So just for everybody, I'll repeat that in a second, but Andrew has his hand up.
Does this spec also allow the system to give answers to questions that weren't asked? To give outputs when no input was sent?
Yeah, so let's look carefully at out of event. Oh, I see. So you're saying, can you just send a fresh, unprompted? Well, what's the spec say? It just says there's no dupes. We don't say anything about there being paired up, right? So from this specification, no dupes in the outputs of the trace. We could have a system that just always, whether it got a message from the client or not, outputs a fresh value. And that could screw a client up, right? Oh, sure. Yeah. Maybe, yeah. So in a richer system, one of the systems that you guys might write this afternoon, we could have this problem. Okay, so there are a couple things going on I just want to mention really quickly in case folks were getting a little lost there. So Adam doesn't like this spec for one reason, which is that it actually just knowing the spec doesn't really tell you if the system does anything at all, right? It's a sort of very coarse safety property. All I'm telling you is that, yeah. The outputs I send to the client, there's never any dupes. There's no guarantee I ever send an output at all, right? So a lot of times, and this should be somewhat unsatisfying, right? Because the whole point of distributed systems, remember, is to continue offering service even when there's failure. So that should give us pause, and it's actually something that isn't in Verity yet, right? This is something that the Ironfleet people have done a little bit of this, but there's a bunch of stuff left in sort of formally verifying those kinds of specifications, that you eventually do something right for real implementations of distributed systems. The second point that Andrew made was that this spec also might be unsatisfying because it's sort of, not constrained enough, right? I might mess up a client because I might send them a fresh message when they're not expecting it. Now, the way we've designed things here, clients are complete black boxes. We can't say anything about clients, right? And this is also a problem, right? So the behavior of a system I might be able to prove something about my interaction with this system if I could kind of inject facts, guarantees about my behavior to the system. Like, look, I promise to adhere to this protocol. I promise not to just send arbitrary input messages. I'll play nice. And if I do that, can I get extra guarantees? There's no way to do that with the way we set up the semantics here. But there is a POPL paper from this January that does it that I'd be happy to chat with people about who are interested. Okie dokie. So now let's try to prove fresh correct.
Sorry, I still didn't follow that. So why couldn't I have a specification that says something about the inputs in the trace as well? It says that
You could. We could have done that.
set up the tier already.
Yeah, we could do that. So sorry, there's two different things. We could have totally written a spec which, there's no dupes in the output, and for every output, every output's immediately preceded by an input. Totally, right? We could absolutely do that here. The liveness stuff is a little bit trickier. And Adam was making this point. So if somebody tells you like, oh yeah, you can almost always encode liveness properties as safety properties, does that make sense to everybody here? Right, so there's liveness properties, maybe, but there's definitely safety properties. Safety property just says you didn't do something bad, right? Liveness property says that eventually you're going to do the right thing, you're going to do something good. So I'm running a distributed system, eventually I'm going to get back to the clients and provide the service that they wanted. Now, I think Adam's point is that, you can encode that as a safety property by saying, well, if it's been too long since I responded, then bad. And now it's become a safety property, right? If you reach that state where it's been too long since you did the thing you promised to do, you're out of luck. Is that fair?
I think this case is simpler because you can just imagine a monitor that watches every step of the system and then runs a decidable property on each one. And that's enough to capture our expectations here. And that's fairly as
for this system, yeah. So there's other systems like there's other systems like Chord and such that are a little bit trickier because the failures are way more nasty. But I agree. I think the vast majority of things people tend to do most of the time, you can encode their liveness properties as safety properties. And the times where you can't, maybe that's not how you should design your system. Okay, so enough hemming and hawing about specs. This is the spec that's on the screen. We're gonna go ahead and prove it. Let's make it look like this might plausibly work. Okay, so what I'm going to try to prove? I'm going to try to prove, look, if I can reach state W, is this buffer big enough? People in the back can see? Is that it?
the right side probably isn't.
Oh, yeah. Oh, yeah. We're actually doing a proof now. We have to... That's what you were waving about. Thank you. Okay, hopefully both sides are big enough. So wait, what are we going to do? We're going to try to prove, look, for any state, W, if I can get to that state with my ideal step, remember, this is where messages in the network get delivered in order, then it better be the case that my outputs are fresh. Right? There's no dupes in the output. Is this going to work? I know you guys are smart. I use the same tone again, so you gotta. So where are we gonna get hung up? What's the problem here?